Well, thanks for coming. I appreciate that. It's towards the end of the Black Hat conference, and I'm delighted to be here for my first ever speaking engagement at Black Hat. I can say unequivocally that this is the most people I've ever seen in one room come into one of my talks. Phil Young and I gave a talk at RSA last year, and there was 7 people in the room, including me and Phil. So this is outstanding. Thank you. Now, most of you are probably thinking, wait, I'm in the wrong room, but you can't leave now. You're in, so you have to stay. And I take the next few slides and just talk a little bit about me before we dive into it. So if I could just draw your attention over to one of these monitors. So I spent prior to the last year and a half, about the last 20 years at a large financial institution, and basically got tired of working for corporate America. And then I reached out to a friend of mine who owns a consulting company in the UK, said, hey, how about we start a franchise in the US for RSM Partners, and I'll run it. And we thought that was a great idea, so we did. So I am the director of operations for North America for RSM Partners, and all we do is mainframe. We do mainframe security, assessments, mainframe software. We do red team augmentation. And when I talk about mainframe, for the purposes of this talk, I am talking about IBM's System Z, running ZOS. There are other things that may be rightly or wrongly considered a mainframe, but for what we're talking about here, we're talking about what is probably the 800-pound gorilla, the most predominant mainframe out there. You may have heard of it referred to as System Z or Z. MVS is the operating system, now called ZOS for the last several years. But that's what we'll be talking about here. So what is this talk? This talk is a year, maybe, worth of research and working on stuff condensed into 40 minutes. It's probably a several-week class if we were to really blow through it all. So I am going to talk about a lot of these things as if you already know what I'm talking about, because I can't go into a tremendous amount of detail. But I'll make analogies wherever I can to things that a lot of you probably do understand if you're not a mainframer. By the way, who in the room would consider themselves a mainframer? You know who you are. That's pretty reasonable. I think I saw 6, maybe 4. Perfect. So all of the mainframers at Black Hat are probably here. I think that's safe to say. But the things that we talk about, not specific to the mainframe, will be familiar to you. So we're going to talk a little bit about the machine itself, a little bit about the structure of it, the CPU, instructions, binaries, vulnerabilities, some of the tools that are out there, how we might exploit and find these vulnerabilities. But there's a lot of 101 stuff out there that I'm not going to go into. You can look at all the people listed there below, have done talks and videos and blog posts and all kinds of stuff. 101-wise on this platform. That's not this. So we talk about the mainframe just as a machine for a minute. If I bring up mainframe to somebody, usually after they ask what I do, the first word, or maybe somewhere in the top 10 words that comes out of their mouth, is this. Anybody know what this is? Yeah, this is COBOL, right? So I say, I do mainframe, and they're like, oh God, that thing runs COBOL, right? It's like, yeah. Is that COBOL? I'm like, well, it's not really COBOL any more than your dishwasher is a fork, right? It's an operating system that runs a bunch of different programming languages. COBOL just happens to be one of them. I got bad news if you're kind of one of these people who's against COBOL, because a great deal of the world runs on it still. In fact, here's a tip, and don't share that outside this room, but if you want to make a ton of money, learn how to write COBOL, because you'll probably never have to ask for another job again. If you ask the media what a mainframe is, generally you'll get something that looks like this. Oops. So IBM released their new flagship System Z this year. It's called the Z14. Has been, by all accounts, just a raging success. There was a whole bunch of news articles about it, and one of them from a really well-known newspaper talked about it, did a great job talking about it, and ran the byline with this picture. You know, I don't know how I'm going to change people's minds if I can't get the Wall Street Journal to publish a better picture than that. But what it really is, if you want to know what it looks like, is something like this. Probably not all that dissimilar to things you have in your data center today. It's a lot of rack full of CPU and memory and a bunch of racks full of storage. It's important. It's really important. So these numbers are over a year old. They've gone up since then, but I didn't feel like updating them. But effectively, from a global payments perspective, the mainframes globally process about $8 trillion. 29 billion ATM transactions, 4 billion passenger flights. These numbers don't mean much to me, so I like to break them down into something a little bit smaller. $8 trillion is the GDP of the UK, France, India, and Brazil combined, or 8 apples. If you're passenger flights per minute, transactions per second. That last one was kind of interesting in terms of the number of global transactions per second. It's about 8.5 times what Google does. I like to use analogies wherever I can because it's kind of it is not pun intended, a black box for a lot of people. I know that the rage today is, full stack developers, DevOps, which in my mind looks a little bit like this. If you think about that from a mainframe perspective, though, is probably a little bit more like this. If you go into a mainframe shop today, what you'll probably find are a bunch of people who are very siloed and very much have expertise in one particular area of it. Maybe networking, maybe security, maybe storage, all working in concert to make this thing sing, make it perform as much as it possibly can. So I'm going to dive a little bit into the architecture, the actual Z architecture, the CPU, and a little bit into ZOS with a lens towards what we're talking about today, which is exploits and vulnerabilities. So the CPU, a lot of people don't know the CPU is a different CPU. It's not x86, it's not ARM, it's Z architecture, right? It's its own CPU. Now it has a lot in common with those other CPUs. It's a von Neumann architecture, right? So you've got data and instructions occupying the same memory space. You can execute data as instructions like shellcode. But it is a different animal altogether. So from an exploit point of view, there's a few things we need to understand. We're always looking at escalating our privileges, so we're going to start at the lowest level and work up. The CPU can operate for any given address, for any given process in a couple of states, problem state and supervisor state. Problem state is kind of normal, right? So problem state is normal. Makes sense, right? Supervisor state is the one that allows you to do pretty much anything you want. Really, the difference between these two states is how many of the instructions that the CPU knows about can you execute. If you're in supervisor state, you can execute the full gamut of instructions. If you are in problem state, you can only execute some of that, some subset of that, especially not the ones that allow you to do privileged executions, for instance. There's one instruction that allows you to move from problem state to supervisor state. So the goal of most exploits or most things we're trying to do is to be able to get to execute that instruction. Simple enough. A couple of other terms we need to understand as we go on here. PSW stands for Program Status Word. So for x86 people out there, this is kind of like a combination of EIP, RIP. It's your instruction pointer, tells you what instruction in memory, what memory address is going to be executed next, and a bunch of flags all kind of smashed together. One of those flags is, is this process that I'm talking about in problem state or in supervisor state? The processor, the current model processor, can run in 3 different modes. It can run 24-bit programs, it can run 31-bit binaries, and it can run 64-bit binaries. If you take only a couple things away from this talk, one thing to help you get into the right mindset about mainframe is it's backwards compatible to a fault. The name of the game, and one of the reasons why mainframe kind of slips into lore as this old technology, this antiquated technology, is because code that was written in the 70s can still run on the very current model architecture with almost, and in some cases, no modification whatsoever. There are absolutely organizations out there running binaries that they wrote 30 years ago that they don't have the source code to. And they just work. It just works. The other thing you understand, so we've got problem state and supervisor state in terms of the CPU mode, is this idea of access storage keys. So when I talk about storage, I'm talking about memory. I'm talking about RAM, okay? part of getting into the mainframe vibe is understanding the parlance that they use for things. And I hate to tell you, but they were here first. So it's not like they're going to change their way anytime soon. We talk about access storage keys. What I'm talking about is for any given address space, for any given process, there is a key, a byte between 0 and 15 that says, simply put, what memory pages does it have access to. Each page of memory also has a key. Basically, if those pages match, I'm oversimplifying this, you might be able to read and write that memory. If they don't match, you're not going to be able to read and write that memory. The exception then is key 0, which allows you to read and write any memory. So the goal from a privilege escalation point of view is to get to supervisor state key 0. I can execute all the things, and I can read and write all the memory. That's just a recap. So that is just the architecture. That has nothing whatsoever to do with the operating system at this point. So ZOS has this idea of operating system integrity whereby it decides through a series of fairly simple rules who can execute in an authorized state. When I say authorized state, I'm talking about who has the ability to change that CPU into supervisor mode or become key 0. There's a few different ways to do that. There are more than I list here, but these are the common ones. The first one, which should be obvious, is in the early IPL process, or the boot process. IPL, initial program load, booting. You boot the mainframe. That all has to run in authorized code because it is the code responsible for setting up the operating system and making sure it can do what it needs to do. At some point in time when the operating system is sufficiently loaded, it gets locked down, and when user land programs start running, then they have a couple of other options if they need to perform authorized functions. They have supervisor calls and program calls. So these can be analogous to what you think about in Linux as maybe a syscall. So if you're writing a Linux program and you have to do an open or a close, socket, connect, those kinds of things, those are things that are necessarily part of the kernel because they have to do very privileged operations, right? I/O to a device, reading and writing from a hard disk, those are privileged operations you don't want average users to be able to do. That's why you have a syscall. You think we're going to talk a lot about SVCs, so you can think about that loosely as like what would be a syscall in Linux. The other construct, which doesn't have a really good analogy in Linux or Windows land, is this idea of an APF authorized library list. So in a nutshell, what this is a list of libraries on the mainframe, and all the mainframers in here cringe when I say this, but a library you could kind of think about like a folder. So it's a list of folders that have a property such that if you can put a binary in this folder, any binaries in this folder can run authorized by definition. So what that means is there's a concatenation or a list of these libraries that's set up on IPL on boot. If you can write to one of these libraries, or if you can add a library that you can write to this list dynamically, which is also possible, that is game over. Because now you can run a binary in supervisor state key 0 by definition. This is how the system maintains integrity. This system ZOS basically says only authorized programs can call other authorized programs unless you meet one of these criteria. I'm going to blow really quickly through the tools, and this is basically just to kind of show you what's out there, and some of it I think you'll find hilarious if you work in reverse engineering or you spend any time in like IDA. It's worth mentioning that the debuggers and disassemblers, for the most part on the mainframe, were designed for people who have the code to the program they're debugging or disassembling, right? Not like reverse engineering or looking for vulnerabilities and that kind of stuff. They don't do a very good job at this, but some of these are really quite clever, so I thought I would show them to you. The first one's called DBX. DBX is a debugger. Actually, I think Oracle has DBX as well. It looks a little bit like GDB. It's kind of GDB-esque. It's nowhere near as functional as GDB. But the good thing about DBX, if you're just getting started in this, the mainframe has a Unix-like interface. It's not a separate operating system. It's just a separate interface to the operating system. It really looks like AIX. DBX runs in the Unix-based operating system, so if you're new to it, like I was when I started this, it's a good place to learn because it'll be the most familiar to you. Debug tool, this one's just hilarious. It's that. I mean, you can imagine staring at that all day long. But there's a lot of limitations to it. You can't do authorized code. You can't do cross-memory stuff. It's super kludgy, but man, those colors are cool. The debugger that comes with the high-level assembler is pretty good. And actually, if you modify it a little bit, you can do authorized code debugging and disassembly. I lived in this one for a long time before I got the one that I use now, which was a third-party product. All of the previous ones are all IBM products. Some of them come with the operating system. Some of them are add-ons. TSOE, test, is kind of an interesting one. It's the original. It's all command-driven. It's the one where if you're stuck on a system and you have to live off the land, if you know how to use it, you might be able to get what you need done. But basically, you type the command TSOE test in your binary name, and then you just get a prompt. So it's a little bit like running GDB without any Chewy interface or Python interface or anything like that. Or as somebody likened it once, if you ever ended up in Linux using the editor ed, and you're like, what the hell is this? I have like one line of text that I can enter and I can't see it when I'm done, and how do I exit this thing? It's kind of like that. ZXDC is the real contender. It's made by a third party, Coalsoft, and it is very good. It has all the features you would want on this platform. It's still text-based on the interface, but it's exceptionally good. It's the one I'll use for my demonstration. So miscellaneous tools. These are things that we find on pen tests on systems that are part of the operating system that can be useful in a pinch. Some of them are really useful. ISR DDN is kind of a handy Swiss Army knife. Lets you look at the concatenations of folders. You can also browse memory, so you can actually browse your address space with this, which we'll show later, which is pretty handy. Disassemble is a disassembler, not shockingly. And A and B list is kind of like an obj dump, OBJ dump that you might use on Linux to basically show you entry points and external symbols and that sort of stuff from a binary. So we can't talk about exploiting and binaries and finding vulnerabilities without talking about the binary formats, just like if we were doing this in Linux and Windows, we couldn't do it without talking about ELF or PE or something like that. So briefly, we'll talk about the binaries and how it works. Generally speaking, the creation of binaries works just like it does on any other platform. You've got source code, you compile it, you get an object, you link it, and then you have a binary. There are a few exceptions to that. And also, it's important that you get the nomenclature. So take our source code, we compile it or assemble it, and that generates program objects. So program objects are non-executable, compiled, but don't have the external references that might come at the time of loading them. There is an option to take those program objects through what's called a batch loader, and it links those program objects and writes them directly into memory. It doesn't actually put them on disk. So you can take your objects, you can link edit them, you can put it directly into memory and execute it right out of memory. That binary never exists on disk. Interesting possibilities. But the more traditional route, you take your program object, you link edit it, you bind it, you create what's called a program module, and then you write that to disk, or in mainframe parlance, DASD, direct access storage device, or the disk. We'll just call it a disk. Program modules then have a couple of different types. So these are the actual executable binaries. Load modules and program objects. A load module is a legacy construct that's been around for a long time. Program object is relatively new, has a lot more features, a bunch of different kind of formats and that sort of thing. I'm not going to dive into these at all, except to say that the differentiation between them has to do with where they land. So if you're creating a binary, whether it's a load module or whether it's a program object, depends upon where that final binary lives. If it lives in Unix system services on the mainframe, or if it lives in a PDSE, it's a program object. If it lives in a PDS, it's a load module. When you upload the slides, I just put these in here so people can look at the manual that basically lays all this out. So if you want to learn more about this, I've got slides through here when I post these. That's like, here's the manual that really breaks all this down. Some really basic assembler constructs. The assembler is very, very intuitive. It's a great assembler language, really intuitive. I find it a lot more intuitive actually than x86 assembler. but a couple of ideas that don't exactly match up here. Store and the instructions that revolve around store have to do with moving something into a memory address. So from a register into memory, or from memory into memory. A load is the opposite. It has to do with moving something into a register. So from memory to a register, from a register to a register. Addressing is could be relative or base plus displacement. So generally speaking, you have a base register, and if you're addressing a variable or something in memory, you have a base register, which is usually set to maybe the beginning of your program, its entry point, and then you have an offset pointing to where your variable or the data you're trying to access. Can also be relative, just like in x86, where I want to say I want to access the thing that's 67 bytes from where I'm at right now. You can do both. This is just an example of an instruction, a common instruction, and what it looks like if you look it up in the manual. They're all documented very well, but just to give you an idea. And then also what it looks like in assembler as well. So this instruction basically just takes a memory address and puts that address into a register. When you look it up in the manual, you'll see the mnemonic right there. Up in the corner, LA for load address, and then you'll see this construct right here, which basically is how you lay it out. You've got the target register, left to right target register, displacement, and then what the base register is to calculate the address from. And then below that, it's got the machine opcodes. So when you see it in shell code or when you see it in machine code, you can know what that looks like. So I've written the same instruction 3 times just so you can see what it looks like in assembler. So this instruction, the kind of like Intel syntax, you've got target, comma, source. So load address into register 4 from my variable. That will get resolved. That gets resolved at compile time, but for readability, you would code it like this. You can do it directly and say, I want to load address into R4 from register 7, which we don't know where register 7 points here, but we know that 1 echo hex bytes from register 7 is also where the address is going to get loaded into register 4. And we can do it as shellcode, and this will execute just fine as well, where we basically just code it in the same format that you see it on the left-hand side. So when we talk about shellcode here in a minute, that's what that'll look like. That is basically just a declaration of a constant, if you will, that has a label S3, and the constant is 4 hex bytes, 4140701E. And there again is the manual if you want to read all about that. Principles of operation is the manual that describes the architecture, describes all the mnemonics, describes all the assembler statements, describes how the system works. It is a jarring read that is really good for insomnia, but it is an absolutely essential reference manual. So when we talk about vulnerabilities, there's a link at the end of this where IBM lists the 6 coding sins on the mainframe. I'm only going to talk about a couple of them for the purpose of this talk, but what you'll find when you look at the vulnerabilities is, by and large, they're similar to vulnerabilities that you would find on other platforms. It might just be called something different, but they're pretty common. Here's an example. So untrusted parameters. So you've got a service call, which is, you'll remember, like a syscall, and that is a privileged program. That is a program that can run authorized. So it's incumbent upon the privileged program to make sure that the calling program, which is not privileged, is authorized to either read or write wherever it's being told to read or write to. So as an example, if I call a service, if I call an SVC and say, hey, fetch me the data that's in memory location XYZ, it's incumbent upon that SVC to make sure that I actually have the ability to read that. If I don't have the ability to read that as my user, it should not perform that action, but we see lots of them that do, right? So I just pass it a memory space and say, hey, read that for me and return it. And if it's not checking to see if I had access, the proper access to that to begin with, if it's not checking my process as key, then I'll just happily return it, and I've got all kinds of vulnerabilities to be able to read memory, right? Read unauthorized memory reads all over the place. The worst one is the converse, which is not checking write access. So that same scenario, I call an SVC, I say, read this memory space, just a byte in memory somewhere, but return it to the pointer in the parameter. I'm going to give you a pointer in one of the parameters where I want the value returned to. If that pointer points somewhere that I don't already have access to, now you've got an SVC that's doing arbitrary writes. And as soon as you can do arbitrary memory writes, that's also game over, just like x86 land. Buffer overflows work just like buffer overflows work. For the maybe one person in here that doesn't know what a buffer overflow is, basically just an unchecked read that's out of bounds outside of wherever it's being stored. So you've got a program, and it reads a 9-digit social security number in it, but the caller feeds it 100 digits, and now you've overwritten memory that you weren't supposed to write to by some 91 bytes. And if you do that right, you can write something important like a return address or a jump address, error routine, or maybe just some important data. The one we're going to talk about today, because it's just fun, is a real live vendor SVC that we found in the wild. We found it years ago. It's since been fixed, but I think it's just great. And it's great for a couple reasons. One, we can show you kind of what to look for, how this works. Frankly, it's still out there. I still find this unpatched version of this. But also, it really kind of lends to what happens if you have people writing critical code for a critical system, but they're not being checked by anyone, whether they're a vendor, whether they are a user. Because oftentimes what will happen, like a vendor might leave literally like a back door in their code so that when they come in and do maintenance, they don't have to go through that pesky change control process, right? Or worry about checking out an authorized ID. They can just use this magic switch to get themselves access to whatever they need. It's also really common to see, especially in today's day and age, where we are working on least privilege, we're locking people out of their authorized IDs, we're not letting you have all that permissions on your developer ID that you used to have. The developers aren't taking that line down, so they create themselves a little backdoor that they can just call periodically when they need to do a thing or another thing. But effectively, it just becomes a giant gaping hole that can pierce the integrity of the system. The one we're going to look at today literally takes 4 parameters, action type, a secret code, which we'll talk more about later, potentially a jump address, and that's the pseudocode in the orange box. It checks the secrets. It makes sure that if the secrets are not good, then it gives you an error and says shame. And if the secrets are good, then you get to steal all the things and everything. Everybody's happy. Maybe not. So I'm going to look at that in 1 minute, but before we do that, I just want to show you an example of what shellcode might look like. There are more succinct ways to do this, but I'm in the idea of like living off the land, keeping it simple, pretty straightforward, but I'll just show you real quick. So you get your working code. This is JCL that's generated from Metasploit. So Metasploit supports this platform. There are payloads out there. One authenticated exploit, a few other things out there. But this is just assembler and JCL that gets generated from Metasploit, put it on my system, compile it, bind it, create a binary. Then I'm just going to copy that binary off to my machine because the manipulation tools on Linux for me are way easier to use than doing it on the mainframe. And I'm essentially just going to take that binary. I'm just going to use a combination of like XXD, grep, cut, that kind of stuff, and make it into a text file that is formatted like a bunch of assembly constant strings. I'm going to put that back up on the mainframe as a text file, and then the only other thing I've got to do is resolve those pesky external functions. So when you write a program, and this is not unique to the mainframe, but when you write shellcode, there's a couple of things shellcode needs to be. One is generally it needs to be a string that can live anywhere in memory, and it has to be position independent, and it can't require any kind of like a loader. So when you load a program, when you execute a binary, it fills in all kinds of information for you about where that function is open and read and all this kind of stuff, because on different systems they might be in different places in memory. That happens when you launch a binary. Same thing happens on the mainframe. So we've got to have functions in here that look that up for us, because we're not necessarily launching our shellcode, right? We're going to be just jumping to it from some area of memory. So we're going to put the instructions in here that do the dynamic lookups, a two-step process. We create the original shellcode. We put these instructions in here that will do the dynamic lookup of those functions. This is a reverse shell, so we've got like a socket, connect, fctl, and then some kind of exec or spawn. We're going to go into the debugger. We're going to find out where those offsets are. We're going to change the instructions, instead of loading from those offsets to just load the address so we can jump to them. And then we're going to zap it. And if you learn nothing else today, you'll learn that the coolest term on mainframe is zapping, basically because it's really, it really is the only cool term on the mainframe. But that basically just means that you're patching a binary, right? So patching a binary, they refer to as a zap, or changing data in memory, they refer to as a zap, which is like super cool. So we're going to find that code that does the lookups on the system. This is the actual code then that does the lookups on the system. And we're basically just going to dump that, copy those bytes, and create shellcode out of that. Now what we've got is position-independent shellcode. So this code now can be jumped to rather than launched as a binary. So here's some examples. I'm going to show some demonstrations. I recorded them because when I get up here, my brain can't tell my fingers what to do, and it's really painful. So on the left-hand side, you're just going to see that shellcode that we just looked at. On the mainframe, I'm going to run that job. On the right-hand side, probably looks familiar to a lot of you. That's just MSF console running a listener, and I got a reverse shell on here just to basically show you what that looks like. The shell is a Linux, or is a Unix shell, so we're operating on the Unix side of the mainframe, but it absolutely is the mainframe and all the permissions of whoever it was that actually executed that shell. So back to this vendor SVC. For whatever reason, in the annals of mainframe history, this has been referred to as the Magic SVC, or a Magic SVC being something that gives you that backdoor, gives you that immediate like escalation to root or supervisor state or whatever. So we refer to it as Magic because when you do it, you get to do all the magic. What we're looking for in terms of a vulnerable SVC is a few things. There's only a few ways to do this transition from problem state to supervisor state. But one of the things that has to happen is there's a bit. There's always just one bit. There's a bit that has to be flipped in your address space for the operating system to say, okay, you can do that. So there's a permission bit, if you will, that says, yeah, this person, this process, this address space can issue the command to move from problem state to supervisor state. So it doesn't actually move you there, it just gives you permission to execute the command. So you could think about it as like the ability to run sudo versus like actually running sudo, right? So if we load up ISR-DDN and we look into our memory where we've got this vulnerable SVC loaded, what we can see, first of all, is there's some text over on the side here, and obviously that text is changed from the original, but it wasn't much different than that, to be honest with you. And then there's another hard-coded word down below, which is, of course, the password. Yeah, so the password required to execute this is just hard-coded in the SVC itself, stored non-encrypted, non-encoded in memory. And it just does a string compare if you type it in and they're equal. I mean, this is 3 lines of assembler code that anybody in here could read after about 5 minutes of instruction. But what I'm looking for is to see if they're doing something nefarious with this or if this is something else. So the first thing I'm looking for is I'm looking for an instruction something like this. So this is an OR instruction. It's an OR immediate. So for you guys out there that are bit twiddlers, if you're doing an OR to a byte in memory, what you're probably doing is changing bits from 0 to 1. So if you OR a byte in memory with some kind of mask, wherever the mask bytes are 1, then the resulting in memory will also be a 1. So this is flipping a bit in memory, and that particular instruction sequence, 960180 Echo Charlie, is kind of hard to read. That is a sequence that I can look for and know that that is probably, not necessarily, but probably flipping this bit. And there are legit reasons to flip this bit, but it's definitely something I would look into further. I'll also mention, in case it went by too fast, that when I went to disassemble this in memory, this warning popped up, preventing me from disassembling it if I don't have permission. Because if you type no, then it won't do it. But if you type yes, it will. So I dump that SVC out of memory, disassemble it, put it into a source library, and then I clean it up. I'm going to rewrite it basically so that I can really figure out what this thing does. I've reversed it, I've disassembled it, but now I really want to understand what it does to know if it's malicious or not, or something that I can exploit. And the way I'm going to do that is I'm going to copy it in and I'm going to use all the macros that the system is designed to do, and then I'm going to go look at it and see, does this look like what was in the memory, what was in memory to begin with? So something like this. So this is the source code after I've rewritten it. of this SVC, and you'll see when we scroll down here a little bit that it's actually using the names that the system resolves for these things. So for instance, there on that OR statement, you'll see it doesn't have register names and addresses anymore. It has something called JSCB ops and JSCB auth. So JSCB stands for job step control block. JSCB ops is a byte in that control block. This is all well documented as part of the operating system. You can look all this up. JSCB auth is the one bit inside that byte that if it's turned on, that is my permission that I need to be able to execute a privilege escalation or change the processor state, if you will. Now, when this was found, I wasn't working there at the time. This has been a while ago. But when this was found, we reported it to the company who is no longer in business but has sold their IP to someone else, and they are still in business. But when we reported it to them at the time, and we explained this and said, look, what you've left behind here is basically like a functional backdoor, and it's not even a good backdoor, right? It's got the password hard-coded in memory, and what it does, which we'll talk about in a minute, is kind of horrific. Like, you know, anybody with a few years of experience or 10 minutes and is halfway smart would be able to figure this out. And they said, yep. Yeah, that's how we built it. It's doing what it meant to be, what it meant to do. This is kind of a cultural problem because there isn't the reason I have the job that I do is because there isn't the hacker ethos, the pen testing mindset. Doesn't exist in a lot of these places. So there's nobody holding these people in check. There's nobody telling them, which you think you wouldn't have to, but there's this whole security by obscurity feeling where nobody's telling them, hey, you shouldn't leave a gaping hole of a back door on production systems at customer sites. That's irresponsible. So that's why I have a job. There's an easier way to go about this. There's a friend of mine named Ayub who was going to present here last year, but he couldn't make it over, couldn't get into the country, but presented it at Black Hat Europe. But he basically has a tool that will just go through and search all the SVCs in memory, search all the strings of bytes, and look for particularly suspicious codes of bytes. It's just a regular expression. And if it finds it, then it will kick it out and say, hey, you should maybe have a look at this. This is kind of suspicious. And then you can go through the whole process of disassembling it or whatever. But it's a quick and dirty way. I use it all the time on customer systems to see if they have anything that looks suspicious. And it does a pretty good job. So back to this vendor SVC, this Magic SVC. It turns out this thing has a couple of different uses. It does a couple of different things. And it is magic. When I tell you about this, you'll be, I'm pretty sure you'll agree with me that it's magic. You call this SVC, and in addition to the super secret password, the one that's hard-coded and stored unencrypted in memory, you pass it another argument. The second argument can be one of 3 values. If you pass it a 4, it flips this JSCB bit on, and basically your address space can now execute the command to move yourself from problem state in supervisor state, key 8 to key 0. If you pass it an 8, it flips that bit off. So you don't want to, if you don't want to leave it on, you can flip it off. If you pass it a 0, you can set the program status word, the PSW. You'll remember that was like the instruction pointer and some flags, to anything you want. So basically it's like a buffer overflow without all the problem, right? You just pass it an address and it just jumps to that address in a fully authorized mode. So this is awesome, right? This is fantastic. It's just a handful of lines of code. This is what that looks like in a debugger. So when I put this in the debugger, what you're going to see is it calls this SVC, SVC 241. When it comes back, I issue the command to put me into supervisor state. Just real quick to show you what that looks like from a debugger point of view when you're actually going through this stuff. So this is my debugger. I'm going to launch I'm going to set a couple of breakpoints. One right before I issue the SVC 241 command. I'm using it in the mode 4. So flip on my JSCB bit. And the second breakpoint, I'm going to stop it right when I issue the command to actually move myself from supervisor state to problem state to supervisor state, key 8, key 0. So there we are, stopped right on that. And now you can see that we're in supervisor state. So super easy, only a couple lines of code to get that point. Okay, then what? Now it's important, and this is a distinction that you might miss if you're not following along entirely, or even if you are, because it's a lot of stuff in a short period of time. But this only is a CPU level privilege that I've changed. So I have changed the CPU to say, hey, this user's address space can now execute any of the CPU's instruction. But we've still got an operating system in front of that. And so my user is still constrained by the security protections of the operating system itself. Just because I'm able to now read any memory and execute any CPU level command doesn't mean I'm able to execute any ZOS level command. But since I can write any place in memory, I can now start flipping bits in my own address space to trick the operating system into thinking that I am allowed to do that. So we go back in here, and the next thing I do after I go to supervisor state is I start modifying bits in my memory. This system runs RACF. RACF is the security manager for ZOS on this system. There's a couple of other products, but this one runs RACF. And basically, I'm flipping the bits in my memory in a data area called the ACEE to tell the system if I try to run a privileged command or view a data set that I don't have access to, it checks a few things. There's a list of things it checks to decide if it's going to give you access to that command or access to that data set. But the first thing on both of those lists is, does this person system special, do they have operations? And those are just bits. Those are just 2 bits in your memory for your address space. They're obviously read-only, unless you are at supervisor state. So now we've got supervisor state, key 0, we can flip these bits, and now I can turn the supervisor state off, and I can use the operating system and all the commands in the operating system to give myself all the privileges I need and go forth. The jumping bit is really pretty cool, because that was one feature of this SVC feature. The jumping bit is pretty cool. So write a program to call this SVC, and I'm going to pass it an address of this reverse shell that we built, and have it jump to it. And when I built it, I just built this function that calls the reverse shell into the source code, but it's an orphan function. There's no way in the source code to actually get to this function. It isn't called to, it isn't branched to anywhere. Just to prove that when I'm calling this SVC and passing in an address and we put the breakpoint back on this function and it lands there, that's how it got there. So what you see here is this is the assembler source code. I'm going to do the branch to I'm going to do a branch to call this Magic SVC. I'm going to pass it the address of my shellcode. And if we look down here at the parameters that I'm going to pass when I call that SVC 241, down in the bottom, you'll see I'm passing it my super secret, and I am passing it right there, and I'm passing it a number 0, and I'm passing it the address of my shellcode. So then there's a function right there in the source code that is that shellcode function. And like I said, there's no way to branch to this. If we end up here, it's because we did a deliberate modification of the instruction pointer and we ended up here. That shouldn't happen. So this is what that looks like in a debugger. And then we'll put it all together. So I'm going to set a breakpoint again before the SVC 241 call, and I'm going to set a breakpoint at this shellcode orphan function. I'm going to run it a couple of times, and what you'll see is after I run it the second time here that it basically lands at the shellcode function right before it calls the reverse shell. So here we are. The instruction pointer is now set to call the reverse shell. And for those of you keeping track at home, I am also running, it's kind of hard to read, but the PSW down there basically indicates that I'm also running in supervisor state. So not only am I going to get this to kick off a reverse shell for me, but it's going to be a fully authorized reverse shell. So when you want to put this all together, obviously, if I'm on a client site, if I'm testing this out, if I find this, I'm not going to do a bunch of, the disassembler and the stepping through this. I'm going to wrap this all up into one tight little package. Usually I have an ID at this point that's not privileged, maybe can't submit jobs, and I want, obviously, more than that. So what you'll see on the next one is basically unprivileged user, bad guy logs in, tries the first thing you usually try when you get creds on a box. Who am I? What do I have? What can I do? He's nobody. He can't really do anything. Calls this binary. Now this all happens in memory, so it is probably not going to set off any alarms. I can tell you it's not going to set off any alarms. Because this is all happening in memory when you log out. If you don't execute any operating system level privileged commands, all these bits are just being flipped in your address space. When you log out, they're gone. Right? So in order to catch this, they would have to be monitoring a whole lot of address spaces and a whole lot of changes, basically real time. So that's what it looks like. So left-hand side is my TSO session where I'm logging in as the bad guy, whose user ID is bad guy. We think they'd be easy to catch that way. And I'm gonna check a couple things. I'm gonna see if I can look at the user, the administrator user, Chad. Can I change my ID right away? Not authorized to do that. I'm just gonna call this one program, and as soon as I do, first thing you'll notice is the reverse shell that pops up on the right-hand side. And then the second thing is I'm gonna start retyping these commands, and now I can list Chad. Now I can change my own user to something more with more privilege. And on the right-hand side, you'll see that I've got a shell, and that shell is also, in fact, authorized. It's a ZOS shell, and I can run commands on there, display my user, and things like that that I would not have had the ability to do. You can see that I've got system special and all that good stuff. So what just happened? So as a non-privileged user, because of a very, very irresponsible piece of vendor code that was left behind, or it could have been user code, but in this case it was vendor code. As a non-privileged user, I basically just wrote a fairly simpler assembler program that anybody with half an ability to write some assembly code could absolutely put that together in short order. Called it, and then I ended up with a privileged TSO session as well as a privileged shell, so I can analyze both sides of the operating system, exfiltrate data, go look for whatever I'm looking for, but basically it's full-on game over at that point. All right, so that was a lot of stuff. I know there's a lot of stuff for you, there's a lot of stuff for me. This is what I would have you take away from all of this if you're not somebody who's going to go dive into the technical end of this. If you're somebody who works in an enterprise that has one of these systems, if you're in the media, if you're interested in this, if you like having money in airplanes that work, this is what I would have you take away. First of all, it's just another computer. It's a big computer, it's an expensive computer, super powerful computer, but it's just a computer. And I say that not to minimize it, but I say that to get people to think about it in a way like you would think about your thermostat, your IoT device, your PC at home, your new robot dog that you bought. All of those things we know are computers, and all of those things we know are written by humans and have vulnerabilities in them, or operated by humans and have misconfigurations. You need to think about this the same way. Second thing is, it's systemically important. I won't go over that again, but it's really freaking important to kind of the world operating as we know it. There's no excuse for this thing to not be a fortress. If you forget everything I said, understand that this thing can be locked down so well that I would have no problem dropping one in DEF CON or on the internet and letting people have access to it and use it in the way it was meant to be used. There are intrusion detection systems, there's full-blown ingress, egress firewalls, there's something called Defense Manager, which can take active action against things that thinks are attacking it. There's 1,000,001 different ways to secure this thing and lock it down. But I'm here to tell you that most of the mainframes I run across, if not all of them, are not. And that has nothing to do with the platform's ability to be secured. It has to do with neglect. It has to do with a false sense of security. It has to do with people thinking like, do we still have mainframes around? Isn't that COBOL? You need to enforce your existing policy in this platform. You've got policies say we're going to pen test, we're going to audit, we're going to do vulnerability management, we're going to do patch management, we're going to have these controls, all this stuff set up on this platform. You need to do that for this platform as well. Get a pen test. Exploits work here, some variation, but they're going to work here, and we can't keep our vendors honest if we don't have people out doing this kind of research. And lastly, it's not COBOL. So that's it. Thank you very much. I think I am right at the end of my time.